So, good afternoon. The group Brahmaputra, is here to present on the topic of comparative analysis of CG TFET and HJ TFET for dielectric label-free biosensing. And this is Madhumita here. Moving on to the introduction part, the figure 1 represents the CG TFET and the figure 2 represents the HJ TFET, where both are compared based on its dielectric modulation. The neutral and the charged biomolecules with different values of dielectric constant are being considered. So here the label-based biosensing relies on the specific properties of label for detecting particular target, whereas the label-free detection is suitable for target molecules that are not labeled, and hence label-free detectors are cost-effective. And looking on to the why FET-based biosensors. The FET-based biosensors such as the field effective transistor biosensors are used because they offer several advantages in detecting and measuring the biological entities. Due to its compact size, label-free detection, physics-based explanations, high sensitivity, fast response speed, the FET-based biosensors have gained popularity in biomedical and analytical industries, contributing to advancement in diagnostic and research. Moving on to the topic of principle of TFET, the TFET is similar in structure of the MOSFET and hence promising for low power. The TFET works on the principle of band-to-band tunneling. It's actually a simple case of tunneling where a particle tunnels from the conduction band minimum to the valence band maximum, which is formed because of the bending of the band edges in the junction region. So the advantage of this band-to-band tunneling is that it offers firstly the low leakage currents and secondly the better subthreshold swings. So the fill factor is nothing but the percentage of the nano gaps filled by the molecules. Due to the partially filled nano gaps, where the dielectric constant in nano gap reduces, it's actually due to the presence of air along the biomolecules, and hence these causes the reduce in the response of the biosensors. On looking on to the 2D Poisson's equation based model of TFET, this actually results in a closed form of equation of drain current, where ID is equal to WT SIE effective EY divided by WT square minimum into AK divided by BK exponential of minus BK into EG divided by Q into WT minimum, where W is the width of the device, TSIE effective is the effective silicon body thickness, EG is the energy gap of the semiconductor, WT minimum is the minimum tunneling width, and where AK and BK are the material dependent constants. So this equation suggests a dependence of the drain current on minimum tunnel width, which in turn dependent on the dielectric constant of the gate insulator region near the tunnel junctions. Therefore, the dielectric constant of the nano gap increases, the minimum tunneling width decreases, and the drain current increases. So the CG TFET and HJ TFET has several and various advantages. The main advantage of the CG TFET is that it has enhanced tunneling probability and its compatibility with its CMOS. The main advantage of HJ TFET is that it has low power consumption and better threshold slope. Moving on to the significance of biomolecules with dielectric constant, it's actually subdivided into two categories. One is the low dielectric constant between the range of 2 to 5, where the dielectric constant is considered to be more consistent. And the other is the high dielectric constant between the range of K is equal to 5 to 12. And it has various and several applications in the real life. Biomolecules along with its dielectrics. So it is said that different biomolecules exhibit different dielectric constant. For instance, the protein has dielectric constant K is equal to 4 and the gluten enzyme has dielectric constant K is between 5 to 7. So different biomolecules exhibit different dielectric constants, and as higher the dielectric constant, higher is the accuracy of the sensing.
In this, I'm In this slide, I'm talk about the architecture of CG TFET and HG TFET. The 2D geometrics, the proposed CG TFET and HT TFET as biosensor are shown in figure 1A and figure 1B respectively. And next figure is tentative fabrication for both the sensor and the architecture of CG TFET and HT TFET are the architecture of CG-TFET typically involves a circular tunnel junction at the gate. In this CG-TFET design allows for improved gate control over the tunneling process, enhancing performance of device. The CG-TFET operates based on quantum tunneling. It carries through the tunnel junction rather than traditional band-to-band tunneling in conventional TETs. The unique architecture aims to achieve better energy efficiency and lower subthreshold swing for potential application in lower electronic device. And the process for formation of CGTFET, the fabrication flow of CGTFET is in accordance with the gate hole formation method. In this method, using dry etching and semicircular window is formed, which can be filled with aluminum dioxide and later etched out to form nano gap for biosensing purpose. The total channel length for all the analysis is kept at 40 nanometer up, which nanogap is 25 nanometer long. In HJTFET, the silicon germanium occupies 5 nanometer of channel length and has 30% of germanium content throughout the analysis. The remaining 50 nanometer is a gate dielectric, that is case equal to 10 for aluminum dioxide. The nanogap is formed by etching out the gate dielectric present in the corresponding area. The thin film of native oxide, that is silicon dioxide, 1 nanometer thick, is therefore considered the nanogap. It's formed as a result of exposure of silicon to air after the dielectric is a result of etched out to form the nanogap and acts as the immobilizing layers of the biomolecules. This is a simulation setup for CG-TFET and HT-TFET used for Centaurus TCAT tool for the simulation purpose. For the simulation of the TCAT biosensor models are non-local band-to-band tunneling and doping independent mobility and high doping concentration are present in the source and drain regions. Therefore, band-to-gap narrowing model is activated. And looking to the result and discussion of this paper, and effect of positions of probes on sensitivity. When the embedded nanogap is filled, considered to be ideal, that is as stated earlier, the assumption that the embedded nanogap is always filled with ideal. And practically, the degree of hybridization of probe and target molecules depends on the location of probes in nanogap. The sensitivity in such a case is dependent on how the probe position influences the operation of the sensor. Hence, the result is higher this biosensitivity. Presence of probe near the tunnel junction of TFET indicates the presence of biomolecules, increase the effective capacitance. Displacement of probes from tunnel junction decrease the sensitivity. And next, status of dielectric modulator CG-TFET and HJ-TFET as label-free biosensor. It shows a sensitivity of CG-TFET and HJ-TFET. There are a number of important simulator and modulator works reported on dielectric modulator TFET and FET. This section presents a map of the sensitivity of such biosensors proposed till date along with sensitivity of proposed CG-TFET and HJ-TFET. And the consideration of different label-free biosensor with a different specification have aided in having an overview of the complete range of sensitivities of label-free biosensor, enabling one to decide performance of any label-free biosensor. Tunnel field effect transistors are more sensitivity to presence of biomolecules than MOSFETs due to the difference in the current injection mechanism. In MOSFET, sensitivities are reduced at lesser channel length. The CG-TFET with a channel length of 40 nanometers shows significant sensitivity. Full nanogap CG-TFET has sensitivity closer to DM-PNP and TFET. Possessing channel length is 250 nanometer and the nanogap length is 75 nanometer. HJ-TFET does not exhibit sensitivity as much as CG-TFET, but similar to DM, PNP and TFET. And this channel length is 100 nanometer and this nano gap length is 30 nanometer.
Hi everyone, this is Ansi Riga, a third year EC student at Tyagarajar College of Engineering, Madurai. So, let's go over the results that was obtained during this study. The third result is about the impact of negatively charged biomolecules on sensitivity. Here, we can see the graph that shows the relationship between negative charge of biomolecules and threshold voltage of CG TFET and HJ TFET. HJ TFET has higher current as compared to CG TFET due to its smaller band gap at tunnel junction, which leads to reduced tunnel width and high overlap of valence and conduction bands. Here, we can notice that as magnitude of negative charge increases, the sensitivity decreases. However, for a particular dielectric constant, CG TFET shows a greater change in sensitivity than HJ TFET with the increase in the magnitude of charge. The change in sensitivity of the sensor with increasing magnitude is small for a low dielectric constant. As the dielectric constant of the nano gap increases, the change in sensitivity reduces. At k is equal to 5, the sensitivity drops by a factor of 25 as compared to k is equal to 12 where it drops by 2.61. Let's look into the gate voltage in different dielectric constant of nanogaps. The voltage balance equation of a metal oxide semiconductor structure is represented as VGS is equal to psi s plus phi ms minus q of minus or plus n divided by C efficient, where psi s is the electrostatic potential at the surface, phi ms is the difference between the work function of metal and semiconductor, q is the value of unit charge, n bio is equal to minus or plus n, which denotes the number of charged biomolecules per unit area, and C efficient is the resultant capacitance per unit area. At a fixed negative n bio and VGS, as k increases, the potential term decreases, resulting in a corresponding increase in psi s. This increases the drain current and hence the sensitivity of the biosensors. The fourth result is about the impact of positively charged biomolecules on sensitivity. Here, with the increase in dielectric constant, the minimum value of drain current shifts to the left, thus verifying the increase in effective capacitance of the nanogap. This corresponds to decrease in threshold voltage with increase in dielectric constant of the nanogap. The presence of negatively charged biomolecule causes reduction in tunnel width. Therefore, the threshold voltage reduces. For k is equal to 5, the sensitivity rises by a factor of 11, whereas for k is equal to 12, the factor is 2.29. The final result obtained is about the sensitivities of dielectric modulated CG TFETs, HJ TFETs and MOSFET. The MOSFET with exactly equal height and length of nanogap as that of CJ TFET and HJ TFET exhibits extremely inferior sensitivity as compared to CJ TFET. Not only does a shorter channel length affect the electrical characteristics of a MOSFET, but also its principles of thermionic emission which contributes to such low sensitivities. On the contrary, TFETs which operate by band-to-band tunneling perform well even when scaled. That's all about CG TFETs and HT TFETs. Hope you liked it. Bye.